Is the audio on? I just saw a message about that. Can everybody hear me? Are we all good? I'm going to dive in and I'll see more messages if we're having audio problems. So just to frame what we're doing today, we're going to spend the half an hour in a notebook. Don't worry, there's no terminal slide deck presentation here. But I do want to talk about where I see what we're doing today fitting into the bigger picture of what's going on with AI right now. We're at DataStax, we're super excited about generative AI, about the agent architectures you can build by chaining LLMs and then using vector DBs to hold context or other things, or doing augmented retrieval. We're not going to talk about any of that today. We're going to talk about the bottom two layers of this picture. We're going to talk about using vector search to generate context or to respond to queries that you're going to deliver directly to whatever your application is. And we're going to talk a little bit about the data layer. To do that, we're going to be working out of a workshop or workbook that we'll share. If you want to go look at it, the DataStax devs GitHub has this in the AI/ML workshop notebooks repository. There also should be a Google Colab link in the notes when they go out. So let's hop over to it. Let's build some vector search. So today we are going to build our DataStax data snacks image search. Yeah, we will. I'll link you out to actually looking at recommendations of similar items. We're going to do image to image, but I will throw a bump in, just reacting to one of the questions. I will throw a bump in at the end about two towers and actually doing different things. But anyway, what do we need to build image to image search? Well, we need some type of model. Previously, we had to build those models. We really don't have to anymore. One of the cool things going on right now is just the absolute explosion of publicly available generalizable models. We're going to use a model called Vision Transformer. There are a bunch of other options. I like this one because it uses transformers, and that's not just because I grew up in the 80s. Transformers are pretty cool. Totally worth reading up on to see why we've had these huge jumps in AI. We're going to use a publicly available image data set to do this for today, and we're going to use Astra DB's vector DB. And in the process of doing this, we'll set up an environment in this notebook. We'll get the image set. We'll process them to extract a vector from our photos. We'll add them into our DB, and then we'll use a fresh image to actually query our DB for similar pictures. And if you like pictures to think about it, here's the classic, what does vector search look like? We're going to do all this today. We're going to take content. We're going to feed that content to our embedding model. In my mind, the embedding model is the librarian at the library I went to when I was 10, and the embedding is the Dewey Decimal System. I think eventually I understood it, but I didn't need to. I could feed my content to the librarian. The librarian could figure out where to put it in the information space that I had. And then if I wanted to query, I could bring my query in back to the librarian, and that librarian could figure out where to look. And then I can look around that embedding and find all the things that look very similar, whatever similarity means, whatever near means here. We'll see a little bit more of that as we go, but I could see all those things and then bring them back as a response to the query. There's a little Easter egg in here too. You'll notice the dots are different colors. There's some very cool things you can do that I will link out to at the bottom of this for embedding multiple different types of things in the same embedding space, like ratings in movies to do personalization. Anyway, let's get set up. As I said, this is all in the workbook. While I run this, let's talk about the libraries we're going to be using. TIMM is used to pull down the publicly available model. Datasets and Datasets Vision will go out to Hugging Face and pull down some of the data models that are available. There are a bunch of great image models out here, or I'm sorry, data sets, not models, apologies. There are a bunch of great image data sets here. We're actually going to be working in See if I see it in this list. I'm going to link to it in the thing too, but we're going to be working out of a image set of snacks. That's probably on page 1. There we go. That way I can make the data snacks pun. Cassandra driver is going to allow us to connect to Astra DB. And in the future, open source Cassandra, if the change goes through and we get that into, that should be on the way, or DataSax Enterprise should all support this. But right now, this is available in beta in Astra if you want to play with it. IPyPlot to make things look a little prettier. Torch Vision, because we're going to have to tweak the images a little bit. PIL, because we're going to want to look at the images. And then we're also going to pull down this ImageNet labels list. So we can talk a little bit about what this model was for and why we can use it to do image-to-image search. All right. If you're following along at home, I have some links out to set up your AstraDB database. Obviously, I've already done that. Our credentials are set up. You'll need to create the AstraDB database. And if you do that right now, keep an eye out for this Try Astra with vector search. We are still in beta. It's not GA. So you definitely want to create a database through here. And there also are some instructions to follow to set up your token and do some other things. Once we've done that, make sure I have what I need. I don't. Just getting my security credentials. I can connect and make sure everything's working correctly. Great. We're good to connect to our vector DB. So let's talk about the good stuff. Let's talk about the data. This is our snacks data set I mentioned. We've got a bunch of images. We've also got a bunch of classification labels. I don't care as much about those today, although I will show you where we see those come up in the data. But I'm not really interested in doing image classification. I'm interested in doing image-to-image search. Also, I should point out that we do have in that data set a couple of splits. We have a test and a validation split. We'll use this test split a little bit later and pretend like users actually uploaded an image, but we'll just pull it out of that part of the data set. All right. Let's import the data set. We're grabbing the big one, and then we'll grab, oh, we got all three because I ran this earlier. All right. Now, because we're working with images, we want to try to normalize the images. We want to get them to a particular image size. We may look at normalizing some of the internals of the image for this data set. This is a pretty typical thing to do. I'm just setting up a transform. And the cool thing with the Hugging Face dataset library is I can just apply that transform to all my data. And let's see where our data set stands now. So looking at an individual row in that data set, we see we've got an image, a PIL image, because it's already been processed. We have a label, and we're already starting to see something that looks like a vector. These aren't actually the vectors we're going to put in the database, but they are the vectors we need to feed to the image model. So this is us pre-processing, sort of setting the size of that image and then prepping the image to feed to the model. And it's just, again, no code at all. There's the 2 tensor that's doing that to get that data transformed and ready. All right, so we have data. We've got some rows of the data. Now we need a model. I'm going to work with this VIT base patch 16224. There are a bunch of other image models out there. If you're doing this for real life, you need to think about some things with the model. How performant is the model? Sometimes a very generalized model like this is not as performant for a discrete set of tasks as a smaller model or a self-trained model. But it's also kind of cool that you can go this quickly and just pull a public model to run with. And obviously, as I said earlier, you know, look for a public model before you dig in to building your own. We are running on the video card. And the model is ready and loaded to the GPU for us to use. So let's look at what happens when we hand our image tensor that we prepared earlier over to the model. We get this completely understandable, you guys know what this means, right? Like, obviously the first dimension of that tensor would be -70 to the 10th minus 1, or -7. I kid, we don't really know all the time what's in these embeddings. It depends. It's based entirely on the model. It's not the original content of the image. It is something that came out of the model where we try to get every dimension here to be independent of the other dimensions. It is, if you start in the mental context of like latitude and longitude for geographic search, and then you just keep adding height and other things onto that, you know, we eventually get to 1,000 dimensions. The cool thing about this particular vision transformer model is that we actually do know what our dimensions are. Our dimensions here are actually those ImageNet label categories and the strength in each of the categories. And I can show you that. So here's an image that I pulled. It's index 10. I pulled from the data. I'm going to pull the tensor out. I'm going to get the actual vector of the results of this model. Let's display the image. And let's look at the top 5 strongest results in that model. So if we look at our tensor, these are the indices in that tensor. Our strongest indices was 582, which is a grocery store at 9.7. But in the top 5, we also saw some Granny Smith. We also saw some orange. We saw some fig, which is interesting, and some banana, which is interesting. Now imagine, not that we just have 5 of these, we have 1,000 of these. And they're not just positive numbers too. We have images in our data set where grocery store is a -4, right? Because it's very not grocery store. And once we start to be able to categorize an image like that, we're actually kind of defining a knowledge space. We're defining a lat, long, blah, 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 out to all the dimensions. We have an orangey dimension, and we have a Granny Smithy dimension, and we have a figgy dimension, and we have a banana dimension. And if we start to plot things across all those dimensions, which is what our vector is, then we could actually look into that vector space and see things like related images. So let's load all of our images through that embedding process. Let's do the inference and get embeddings for all the images. This is going to be about 5,000 images that we do embeddings on. It's probably a minute if you have a GPU. It's probably 40 minutes if you don't, which is fine. If you're out on Colab, you can run this either way. And then the next thing we would do is we'd actually save our embeddings to Astra DB. And this is where we're taking all that cool embedding stuff we did, and we're saying, all right, we're going to have a photo app, and people can upload images, and they can see images that are like the image that they had, and you know, it's out there for everybody to use. And we're not going to run that with our, you know, we're not going to train and load the model and load all the images every time we do that. We need a persistence layer to operate our vector search against when we roll this out into the big world. So if we, so the way we do that is we're going to create a key space and a table, or we're going to create a table. We already have the key space. Inside Astra, it looks a lot like, if you know SQL, this is Cassandra query language, but create a table, key space, table name. I've got an ID. I've got an image vector. And that's all I care about right now in terms of storing this image in the database. In the real world, you're going to have metadata. You're going to have other things. Maybe you save them in the same table. Maybe you change your model a lot and you don't save them in the same table. You save them in a different table to look up. But for now, this is all we need to get started. So create a table, create a custom index. We're ready for data. This process currently, because I'm not running multi-threaded, takes about 40 minutes. So I'm going to do the classic cooking show trick and tell you that I already have a cake in the other oven. So we should be able to query against that data because I've preloaded it. So we're going to do a query for item number 422. We're going to grab that item out of our test data split. This is not part of the data that we did embeddings for and put into the vector DB. We're pretending like this is a fresh upload or some image that somebody just gave us. We're going to take a look at what that image is. We're going to get the embedding for that image, and then we're going to take that embedding and we're just going to do select ID and image vector from our vector table, order by the image vector for anything that's an approximate nearest neighbor of that 1,000 dimension embedding, and let's get 5 of them back. And let's see how well that worked. I mean, think about this in terms like this is a 15-minute setup. Public model, public data, take an image, couple of lines of Python. I've got the image ready to train, but did it work? So here's our original image, and here are our matches. This is a great match. The first one, you can tell it's a slightly different image, but it's got all the same elements. The second image is a little more cryptic. This would be fun to dig into and see. We've got some similar shape things, but clearly a banana is not a hot dog. But then the rest of our images are really solid hits. Yes, no, this is not a hot dog. The others are really solid hits. Well, we have seen this app, but we saw this app as image classification. Now we're doing full search. Let me try a different one too, just to give you an idea that this is just not the magic of a well-rigged demo. So we'll do 120, which looks like a birthday cake. Ooh, I hate these. But we did get a birthday cake back here. Be fun to break down our nearest neighbor on this guy and see. We could use the code from earlier if you have this notebook and you want to actually investigate the major categories for each of the hits. Here's some apples. We're usually really good about apples. I don't know if I'd be too impressed by this because apples are usually what we get back for just about anything. And here we go, cupcakes. There we go. Pull down the notebook, play with this, run it on the free Google Colab, set up an Astra account, and the rest of it you can just run through with a database, start doing image search, tear into these guys and see if you can see why they matched or why they didn't. Feel free to play with this or share it around. If you want to go forward from here, I have a couple of maybe branching paths depending on what you'd like to dig into more deeply. So if you'd like to do a little bit more deeper into vectors, Google's got this great developer practitioner class that really digs into what vector embeddings are. If you want to go have coffee with data scientists, there's a great machine learning crash course. I had to relearn a bunch of math that I had forgotten about. And the funny thing about the crash course is it starts hard and it gets a little easier. If you want to embed two vectors in the same embedding space, this is a recommendation engine. We're really talking about two towers as an architecture, and there's a great blog on Google that'll start you on that path. If you want to go the other direction and build up to generative AI and agent architectures, check out the Cassio.org site. There's a really funny story about how this derived out of a hallucination when Patrick McFadden was digging into how this stuff works. And then if you want to dig deeper into the vision transformer, there's a nice workbook that's a walkthrough here. That's it. This is a lightning run through image to image search implemented on Astra's new beta of vector search. And it's available, as we said, in the notebook. Take it, play with it, send me some feedback. I'm happy to hear whatever about it. I'm curious what people find, what folds they find in the data. If they play with other image models, you could rework this for sound very easily. Obviously, people are doing a ton of things with text. Let me see if there's anything interesting in the comments, or Patrick, if you've seen anything out on YouTube, I'm happy. We've got a couple of minutes. We could hop into that. Yep. Any questions out there? I could have used image to vec. The question is, why didn't I use image to vec? I could have used image to vec. I wanted to use a model that actually used transformers, and that's the whole reason that I picked VIT. But image to vec would have been fine. I'm trying to remember what the other one is. Efficient net is the other one that people like to do a lot. This is for Andy's question about why we didn't use image to vec. Anything else out there? We've got a Colab URL in the questions. Hey, Patrick.
Hi. So yeah, I thought I might jump in here with my own because I can do that.
Yeah.
The question I'm gonna come up with here shortly is probably one that I hear a lot is like around, is there best practices of for vectors, especially when using Cassandra? And I may be kind of leading the witness a little bit.
The big one that hops out to me that may not be the answer you have a lot is the dimensionality of the vector is going to affect how performant the search is.
Yeah.
One of the cool things about vectors that I didn't get into here is vectors can actually sort of decrease your feature space. They can fold your feature space a little bit. So if you're building something complicated and it needs to be fast, then you need to use that ability to get down into 50 dimensions or smaller than that, because all your interactions are going to be a lot more performant. And you're probably going to be living in this experience of like a bunch of the text embedding models are 768 dimensions, a bunch of the images are 1,000, and like there's a performance impact to the generalization of the images. Less is better. More is probably more generalized and flexible, and you're getting the benefit of work other people have done.
Mm-hmm, mm-hmm. Yeah, I think it's worth mentioning too that the underlying indexing scheme here is HNSW from Lucene, and so a lot of those anything that works there works great. This is what works great with Cassandra because it's the same library.
Yeah. Worth understanding that too as you dig into it, because in my mind, I'm just doing cosine difference between two vectors, but you can't do that with 1,000 vectors. Like it's not performant. So you get into this stuff like HNSW, which may also be why we saw the bananas on that hot dog search. HNSW can jump around a little bit for its ANN.
Yeah, and there's a difference between the indexing types when you create the index. And of course, you didn't go into that piece so much, but there are two different types of indexes you can create. The dot product and the cosine. Cosine is the default, but dot product is like twice as fast.
And it returns different results too, because the math is a little different. And I've seen a bunch of recommendations about play with that too, particularly if you've got a good test set and you have a good judgment list. I would throw into at a very high level, if you're going to work with this, go look at some of the work that Open Source Connections did with Cupid, which was a way to build judgment lists against traditional search. But I think that approach is going to be a big deal as we get into things like vector search, where we need to evaluate a model really quickly to figure out how effective it is for the searches that we know people are going to perform.
Yeah. Well, this kind of underscores this thing. It's like, I feel like a lot of folks, especially maybe even in this particular workshop, are pretty new to this concept. And that's okay. Hey, we're working through this as a community. I think vector was a niche for a small group of people that were using it really highly effectively. Like if you worked at Meta, but now we're all having to get thrown into this. So this is good. We didn't just share information like this.
I touched it a few years ago with the Vespa database when I was doing search stuff, which was neat, but like it wasn't there yet. And it seems like it's there now.
What do you got for
Just
scooters?
imagine that idea, like image to image search on Apache Cassandra. Like Apache has that scale. It, you know, it runs the deep beating heart of the internet, and then just be able to lay something like this on top of it, or, you know, large language models, or image to sound, or some of the stuff that's a pretty well trod path, like what Netflix did with recommendations, where you're laying ratings in the same embedding space that you're laying movies, or you're laying users from their features in the same embedding space that you're rating movies, and you can just get a brand new user, grab their features, run it through the model, and get back a bunch of movies that seem like they're close to that user. That's amazing.
So while we've been chatting, all of a sudden the questions have rolled in on the chat. We should go look at those.
Yeah.
Real quick. There's some good ones in here. Like Stefan is like, does this work for a recommendation of similar items like documents, depending on content?
Yep. So that's a multimodal model, and look at two towers to do that. You got to train it to do both of those, and you've got to have a classification system that like lets you compare apples and oranges, not just images of apples and oranges. But once you do that, it's really powerful for, like, I don't know, just crazy things. Like we could have a set of features around soil samples, and we could have another set of embeddings around geographic locations, and we could take a soil sample and guess where it probably came from, because we embedded those two vectors in the same embedding space. There are a bunch of cool things that can happen there. I think Spotify uses that for a bunch of their recommendations now, and has been for a while. Not on Astra DB yet, but we'll get them over here. There are a bunch of use cases already where people are doing multi-embeddings.
Yeah, the semantic search, and that I think there's a lot of questions along this line. Yeah, and this is Elasticsearch now includes HNSW from Lucene. Surprise, because it is different. But it's context, and I think that's one of the main differences you can get out of the search. So if you have a block of text, instead of searching for the word cat in it, which, you know, standard text search does, you can look for context. Is this about a cat, or does it just happen to mention a cat? And
it just starts there, man. I didn't do this with this
all fired
example.
up.
Say I took one of those images and I wanted an apple with a lemon, and I knew the vector for an apple image, and I wanted to find ones that had lemons with the apples. I know what those feature vectors are for this particular model. I could do a query and just bump the lemoniness up, and I'm translating to a different place in the vector space, and I'm getting a similar image with a new element in it. Like, you're right. Similarity search is awesome. The way the models find latent connections between the data and then surface them so we can work with them. But we can also do translations and play games in that vector space. They're really kind of cool.
Yeah. So let's see if we can tackle a couple more questions here.
Yeah.
Because boy, they're just starting to stream in now. This should be a streaming workshop. That's the next one, by the way, everyone.
Yeah.
The streaming.
Pulsar's awesome, guys.
Is there any other workshops about vector databases? I'm going to be careful. Vector search is really the feature that we're looking at here. But yes, I will look for the link real quick, or if someone out there already has it. There's it started yesterday, but you can catch up. There's a 5-week series on using LLMs and Cassandra and Vector to basically build your own ChatGPT. So much more comprehensive. I will find the link and put it in here.
Yeah, that's that high-level Gen AI agent architecture stuff. That's so cool.
Yeah, exactly.
There should be a bunch of information about vectors for recommendations. Like I said, Google's got a bunch of information about it. And if you look around a little bit, I don't know, do we have anything about pure vector search, or most of our stuff right now is Gen AI and
it's mostly Gen AI because it's using vector search. It's vector search in general needs a use case, right?
I see a couple of questions about combining other metadata. Absolutely. You can put anything you want in that table. I just did the ID and the vector because that's all I needed for the search. I even like did a little trick where I didn't bother saving the images anywhere because I had the original data set. You could put whatever you want in it, treat it like a normal Cassandra table, and then just access it through vectors. In the long run, I feel like embeddings are going to change. So maybe you'll have your metadata in one table ID'd and your vector in another table, but it's hard for me to predict.
Yeah. So then there's a question. I think we answered this before. I just want to make sure this is clear. Apart from cosine similarity, what other algorithms? There's dot product. Yeah. And that's in the docs, but the caveat is cosine can work with any amount of dimensions. You don't have to have the same amount of dimensions. So if you have 1,000, 500, whatever, dot product absolutely requires the same amount of dimensions in every.
That breaks my brain.
Yeah. And if you don't, then you won't get normal. You won't get rational results.
Well, it's hard enough to reason about this without having different sets of dimensions.
Right.
Somebody asked about batch insert. Everything right. Batch insert is a little bit subjective in Cassandra because it's really only worth doing when like you're sharing partition keys. It exists. There are also some talks about definitely in this model training, switch over your embeddings workflow, the ability to load data really quickly, which Cassandra can already do, tens of thousands, hundreds of thousands records per second. Maybe we want to go even faster. So keep an eye on us for that because there may be some stuff coming out to do even more efficient batch.
All right, there's a couple more in here, I think.
I don't know how to compare it to PG Vector. We're still in beta. I'm sure those numbers will come out. It's on Cassandra, so I'm optimistic that it's going to tear.
I think that in general, PG Vector, if you're looking at the algorithms, HNSW from Lucene is a really optimized library. So we're pretty happy that we're using that one. PG Vector uses a different one that there's a ANNbenchmarks.com or .net. Anyway, ANN benchmarks out there. If you want to do some comparison on different algorithms and indexing schemes, that includes things like FACE, HNSW, there's ANNlib. There's a ton of them. But yeah, well, here we are. I mean, it's getting mainstream when we have sites up that compare speeds.
Yeah, it's got to happen now. Ridvik had a question about no host available. That probably is just the Secure Connect bundle that the step before that downloads. So make sure you run that step and then pick the database you want to use from the dropdown from the Astra databases you have, and then click the download button. You can also look in your files in Colab and make sure there's a Secure Connect bundle file in there that's actually used to do a secure connection to Astra. It is funny that the vector search is much easier than the Secure Connect.
Yeah, that's funny. That is funny. So then the last one, which I think is interesting, is can you invert the vector so you can find out what the image is about? I think I know how you could do that, but Matt, I bet you have an even slicker solution.
I don't know, but in this particular model, the cool thing is I can just look in the vector and find the dimensions with the greatest magnitude and go pull that ImageNet classification, right? So that you see it in the top K example that I did where I bring back this category, this category, this category. It's not always that easy to look at a vector and actually figure out what it represents. But here it's a pretty clear delineation. And you, as I mentioned earlier, you could also do things like poke at those values to try to find other images that are more lemony or more grocery story or whatever. It's not stable diffusion. But you could explore that space by playing with the vectors.
Yeah, that's interesting. So we're gonna have two answers. I think one of the things that you could potentially do, and we should probably end this soon, but you could also, there's libraries out there that will contextualize a picture. So that would be a transformer that would say, take a picture and then create a text description of it. Those transformers do exist. And then you would take the text description and vectorize that.
By the way, that's That's a multimodal embedding where you've embedded your images and your text in the same embedding space so that you can take an image and pull back text results. Very cool.
Yeah, it is very, very cool. I think we're at the end here.
Yeah. If you have any questions, I should have put it on the slide. It's matt.overstreet@datastacks.com. Happy to answer questions by email or reach out on LinkedIn or whatever.
Yeah. Thanks a lot, Matt, for a very insightful workshop.
Thanks, Patrick. Fun setting this up. A lot of
Thanks,
good
everyone.
stuff is going to happen here.
We'll see you soon. Next 2 weeks, we're going to be doing streaming. We'll see you there.